Next, we can investigate the velocity profiles at different points along the length of the artery. To do this, we again need to create planes on which to plot vectors. In the top bar, select Locations as before, and click Plane. Name this Sec Plane 1. In the Details pane, ensure Method is XY plane. This lets us define a plane parallel to the origin XY plane using a given offset. Enter -0.02 for Z. And click Apply to create the plane. Repeat this process to create another plane by again selecting Location and clicking Plane. Name this Sec Plane 2. As before, ensure that Method is XY plane and enter 0.005 for Z. And click Apply. Repeat this process one more time. Name this Sec Plane 3. With Method set to XY plane, enter 0.015 for Z. And click Apply. This has created 3 planes that we can create visualizations on. We will start with velocity vectors. Select the Vectors option in the top bar as before. And name this Sec Plane Vectors. In the Details pane, next to Locations, click the 3 dots. In the pop-up window, we can see a list of surfaces on which we can plot vectors. Hold Ctrl on your keyboard. Left-click on the 3 section planes we just created to select all of them. And select OK. Back in the Details pane, ensure Variable is Velocity, and click Apply. In the outline, we can adjust our view as before by ensuring only Sec Plane Vectors and Wall are checked. We can now see vectors along these section planes. This gives us a good sense of the velocity profiles in each of these sections. Right at the inlet, we would expect a constant, flat velocity profile, but as we move along the artery, the boundary layers begin to develop, and this profile will start to get more rounded. We can see this along the first section plane. The boundary layer development along the sides from the no slip condition has made the velocity small near the edges, and the profile is pretty rounded. It is, however, approximately symmetric along a center line for the main passage. As we move closer to the fork, however, the symmetry is lost. The velocity becomes much higher near the inner walls, and the profile becomes skewed. As we move even farther towards the outlets, however, the profile has generally recovered to the typical symmetric profile, as is typical of pipe flow. This matches our expectations from pre-analysis. Another useful visualization is streamlines of the flow. This allows us to get a clear sense of how fluid particles move along the artery. Start by selecting Streamline in the top bar. Name this Streamlines. In the Details pane, change Start From to Inlet. This means that the post-processor will release particles from the inlet boundary and use the velocity directions along each cell to integrate the path. Ensure sampling is equally spaced. We can now select the number of points on the inlet that the post-processor will track. For simplicity, we will visualize 2 particle paths. So enter 2 and click Apply. In the outline, ensure only streamlines and wall are checked, so you can uncheck section plane vectors. We can then see the particle paths in the view and see how they vary along each path. If we use the middle mouse button to rotate the view, we can also get a better sense of the full 3D motion of the fluid. For more complete views, we can adjust the number of points to include more and more streamlines. I encourage you to experiment with this yourself. We can use the planes we created before to get a deeper understanding of the flow domain using contours. Start by selecting Contour in the top bar. Name it Midplane Velocity. In the Details pane, under Location, make sure Midplane is selected. Ensure that the variable is set to Velocity, and change Number of Contours to 101. And click Apply. Repeat this process to create another contour plot. Name this Midplane Pressure. In the Details pane, ensure Midplane is selected under Locations, as before. Ensure Variable is set to Pressure, and change Number of Contours to 101. And click Apply as before. In the View pane, Change it to include 2 side-by-side views as before. Left-click in the first view, and ensure that only midplane velocity is selected. This includes unchecking wall. Similarly, left-click in the second view, and ensure that only midplane pressure is selected. Click on the y-axis in the bottom right to fix the view if necessary. This lets us better investigate the velocity and pressure distributions in the artery. As with the volume renders, we can see the low velocity and high pressure region created near the branch from the stagnation point. We can also clearly see the effect of the separation region on the flow, creating a low velocity region that is not recovered in a high pressure region because of the viscous losses. Looking near the inlet, we can see the boundary layers developing along the sides of the domain, creating low velocity regions near the wall that grow over time. We can also see that this causes the velocity near the center of the artery to increase slightly above the prescribed inlet velocity. From the pressure plot, we can see pressure generally decreases over time when moving towards the outlet. A similar process can be completed using the section planes we created earlier. As before, create a new contour plot by selecting it in the top bar. Name this sec plane velocity. In the details pane, ensure variable is set to velocity. Next to location, click the 3 dots. Click on section plane 1, and then hold Control and select the other 2 section planes. Click OK. Back in the details pane, change number of contours to 101 and click Apply. Repeat this process again to create pressure contours. Name this sec plane pressure. In the details pane, ensure variable is pressure, and click the 3 dots next to locations as before. Again, click the first section plane, hold Control, and select the remaining 2. We can then click OK. Again, change number of contours to 101 and click Apply. Left-click in the first view, and in the outline, ensure only sec plane velocity is selected. Left-click in the right view, and ensure only sec plane pressure is selected. We can then use the middle mouse button to rotate the view and see these planes. Near the inlet, we can see the boundary layer development along the sides. The profile is approximately radially symmetric. The pressure, however, seems to be constant along this plane. Near the branch, the velocity contours show that the profile begins to skew, as seen previously. In the pressure contours, we can see the high pressure stagnation region, but the pressure is otherwise constant across the plane. Near the outlets, we can see that the velocity profiles have recovered to a distribution that is more similar to the inlet. The pressure, again, is approximately constant across the plane. Looking at the pressures together, we can see that the pressure remains approximately constant along each profile, but decreases as the flow moves towards the outlet.